into maybe the rest of the session, where we can talk a bit more about open problems. What have we learned from this workshop, and where could we maybe go towards in the future? Maybe even organizing other types of workshops. Before I briefly tell you about what we've been up to and where I think are really important problems, specifically in the area of equivariance in 3D and for computational chemistry, I wanted to actually kind of explain a bit to you where I'm coming from. So why do I think the types of problems that I will talk about later are actually super important? And so my group has been working in many different areas with collaborators in trying to use machine learning to run simulations. Yeah? So simulations is essentially the problem of solving differential equations. Yeah? So all of the systems that you see here, like a protein, for instance, the movement of a protein, fluids, governed by something like the Navier-Stokes equation, but also robotics, which are typically, have to operate within some sort of Newton, in the context of some form of Newton mechanics. They are all governed by particular types of differential equations. We do know the differential equations, but solving them, so simulating these systems, is really difficult. And so that's where machine learning comes in. And I just wanted to give you this really high-level intuition of like, how can we actually use machine learning, or what is one particular application of machine learning in the context of simulations. So for instance, and this is what I will also talk about in terms of our research, if we want to simulate molecules, so atomistic systems in general, like for instance, crystal structures, but also larger biomedical molecules like the protein that you see here, they're governed by the Schrödinger equation. We need to use some sort of quantum mechanical inspired methods, like for instance DFT. Many of you might have heard about this. This takes weeks of computation on a supercomputer, and also typically just scales to very small molecules, up to maybe a couple of hundred atoms. And so the idea now is that we actually can use these very expensive ways to generate data. So typically what we need for molecules, if we want to actually train a machine learning model, are the forces on the atoms and the energy of the entire molecule, which we can then integrate, and so therefore kind of move essentially the molecule through a simulation. And so what we would do typically is we use an expensive method to generate some training data, so a particular 3D point cloud. So this goes back to what we heard about before in previous talks. So a 3D point cloud representing the molecule, where the atoms are XYZ positions in 3D, and also the atom type, like carbon and hydrogen. We would send this to such an expensive method, and this expensive method essentially gives us the forces on the atoms and the energies. And so now the idea is then that we can train a machine learning model, and then we can use that machine learning model actually for simulations. And so this is actually, and also going back to some discussions that I had, quite different to the setting where you say, I have a training data set and I have a test data set, and I just want to be kind of good on the test data set. Because when you run simulations, you might actually encounter, because you're kind of moving around and changing the structure of this molecule, you might actually encounter particular configurations that you haven't really seen in your training data. And that's also the argument why here specifically equivariance with respect to, for instance, the rotation group, translation group, and so forth, is really important. So there's this debate, and I will also talk a bit more about this. Hannah mentioned this already in her talk. Do we actually need equivariance? And I think here really it is super important. Yeah.
Do people give guarantees for the outcome of this, or they don't care?
What do you mean by guarantees?
Like error bounds or confidence bounds and stuff like that?
No, because so typically what you do is you train the models, and then you run the simulations, and you check essentially, based on some test data, of course, whether the energies and forces are fine. And you also can run simulations where you have experimental data. So you for instance, want to determine the density of some sort of liquid, and so you run this, you know what the result should be, and so you can kind of also check by doing this if this trained MLIP, so machine learned interatomic potential, does actually do a good job. Yeah, but in a sense, the idea is that no, typically you cannot actually have any guarantees. Yeah, but so the computational chemists that I talk with, they're very excited about this, and it's really actually heavily used also now, yeah, by the domain experts. So they're really enthusiastic about this. Yeah, and so of course one of the other advantages is that now, because there are lots of people are running these expensive simulations and are collecting data, that you have more and more data sets out there that you can actually use for things like pre-training, training, quote unquote, universal models like foundation models and these types of things. So that's kind of a very big topic right now in this area. And so there are two main problems. And this goes a bit back maybe also to your question. Yeah, so if we kind of just train naively some machine learning model, we might get very poor generalization. I mean, that's generally a problem, especially when we just train this on the available data. So typically what you have to do is if you want to apply them to a new system, you have to generate data for that particular atomistic system, just a little bit to fine-tune essentially the model. And if you generate these like brute force, these data sets, it's also typically too expensive. So you have to be careful. Yeah? So here we don't really oftentimes have this bitter lesson where we have a ton of data laying around and we can just kind of scale up a transformer model to do well. Yeah? So this is another reason why equivariance here is very important. And that's precisely what people have been looking at. So how do we actually make these models generalize better? Yeah? Be more robust when we actually use them in simulations. And there's kind of two ways that people have followed largely. One is include physics-aware inductive biases. So when you talk to these people, for instance, SO3 equivariance to them is a physics bias. Also, typically there is the bias that you predict the energy for the entire molecule, and then you take the gradients of the energy with respect to the positions, the XYZ positions of the atoms to be the forces. So you have this kind of guarantee of energy conservation when you train these models like this. So a lot of work kind of goes into understanding how can you actually make these models more physics aware. Because the idea is if you run them specifically in simulations, this is actually working better. The other area which we also work in is not so related to this workshop, which is about the data generation. So how do we actually do this? Okay, so I just very, very briefly, for just a few more minutes, kind of wanted to give you an intuition a bit more, like what is it actually that we do here? And when I first kind of started a few years ago, talked to people in this area, I was kind of surprised about how similar the problems that they think about are to our problems. So because, right, what you see here is essentially like two possible kind of variables that you have in this molecule. Like for instance, you could maybe like rotate this molecule around this particular bond. These are these little Greek letters that you have here. So one of those angles could be here, another angle could be here. And then depending on how you kind of rotate those, you get different potential energies. And the way that you can think about this is, right, that if you, for instance, have particular atoms very close to each other, even though there is a repulsive force between them, is that then the potential energy increases and the forces that are kind of acting on these atoms to kind of push them apart again increases. Yeah? And so what you see here is the so-called potential energy landscape. So again, here you have kind of like your input, and in the most extreme case, this would just be, of course, a very high-dimensional manifold, where you have all the possible XYZ coordinates of the atom, and then to each of those you have essentially a particular potential energy. And the connection to machine learning is that, in a sense, oftentimes we have the weights, on the XY axis here, and we look at a particular loss. But what chemists are also interested in is to actually find minima of this landscape, in the same way that we machine learners try to find minima of this loss landscape, and the minima correspond to the most likely configurations of these atoms, of these molecules. So the equilibrium configurations. Another really important problem here is if you want to study reactions. So you want to understand, how can we actually accomplish reactions from one a particular molecule to another, or a set of molecules to another. And reactions, if you want to study them, are corresponding to saddle points on this energy landscape. Yeah, because typically you have some sort of low energy configuration that's stable, and you need to bring this over this kind of saddle point into another low energy configuration. Yeah? And so again, most of computational chemistry is kind of concerned about mapping particular 3D point clouds, so particular configuration of these molecules, to the energy and the corresponding forces that act on the atoms, to then use this for some sort of problem. And the simulation here means you're sampling essentially from the distribution that's proportional to the negative of this energy, so the so-called Boltzmann distribution. And by sampling from this Boltzmann distribution, you can essentially compute any type of property that you might be interested in this molecule, like is it solvable, what is the density, and so forth. Yeah? So this is kind of the setup of what a lot of people are working on. And now we are coming to the connection to this workshop. If we want to predict, for instance, using some sort of message passing neural network, for instance, forces, we want that the prediction of these forces are equivariant to, for instance, rotations. Yeah, so you can see this here. So if you rotate the molecule, you also want to rotate the forces in the same way. And then we also have the notion of permutation equivariance on particular atoms. Like, for instance, these two hydrogen atoms here are. Yeah? If you permute them, you also want to have exactly the same energy and exactly the same forces on the atoms. And so now this slide essentially goes back to the presentation of Hannah from a few days ago, where people have now thought about, okay, how can we actually build message passing neural networks that actually capture kind of the geometric environment of particular atoms. And the way that this is done is typically, and this is also what Rizi presented, is that you kind of construct, so typically you have a point cloud, you don't already have a graph. So what you do is you take a radius and you connect essentially the central atom to all of the other atoms within this radius. And then you have essentially two different types of features. And this goes back to a discussion that I had with Misha, and which I think is really interesting. So in the work that I've seen also from Nadav is that you typically think about just taking the distances as an input, as features. But this is just one type of feature that you have. The other types of features are actually the vectors, so the directional information. Yeah, so you kind of normalize these vectors to have unit 1. And so these are the other types of features that you essentially put into this model. So not just the distances, but also the directional information. And this directional information is encoded using what's called tensors. Yeah? So these kind of multidimensional objects. And depending on if you're in what kind of basis you're working, what type of method you're using, you are creating these so-called irreducible representations of these vectors.
Yeah. So just a clarification. So you're saying direction meaning angles of the distances. Is that what you mean? Or?
Essentially. So it's essentially the vector that points from the central atom. This is the better one here. It's the vectors that point from the central atom to its neighboring atoms. But as a unit vector. So you can think of it as angular. If you normalize this, it's like an angular information, exactly. Yeah, and from those you're actually constructing these so-called irreducible representations. And so yesterday, it wasn't yesterday, it was a couple of days ago in Hannah's talk, we saw now that we can kind of understand the different types of methods that have been invented in this community by looking at the tensor order of the features. Yeah, so how do we construct these kind of tensors here based on the directional, so the angular information that we have? Also the many-bodiness. So since you're working in this community, have heard about these neural networks that look at angles and dihedrals and explicitly use them as features, as input features. And so you can see how this gets also then, of course, more and more expressive. So here we have really many dimensions of expressivity in a sense, not just one. And so the nice thing is that, so there are particular methods, and one direction is based on spherical harmonics, which was presented by Hannah, where you can essentially build these message-passing neural networks, which implicitly capture, by computing these tensor products, by implicitly capturing essentially kind of many body features, yeah, even going beyond dihedrals. And so this is one of the things that we actually worked on. So maze is a pretty popular, kind of powerful, very expressive model in spherical coordinates. And we have essentially proposed last year the equivalent, but in Cartesian coordinates. And when you now look at so the question is like, why would you do this? Yeah, we are not really necessarily getting more expressive, but you can see that the kind of computational complexity in computing these irreducible representations, these irreducible tensors, and computing the vector, the tensor product between them, has different complexities depending on whether we go to spherical coordinates or we stay in Cartesian coordinates. And because oftentimes in many applications, we need a small l, so yeah, something like smaller or equal than 4. Actually, this can actually be beneficial, and we have shown that in many cases it is actually more efficient to use this than to use something like maze. Okay, so this is just kind of to a bit, set the stage to the types of research question. Also, kind of the impression that I got from the workshop, which I now want to talk a bit about. So first of all, just to reiterate a bit on this, I think what's really nice is that this is a community that really thinks equivariance is extremely important. Yeah, so they really don't believe in this hype where people say, oh, we don't need this anymore, we just need to scale. Precisely because generating data here is actually difficult. So if you now think, for instance, about something like AlphaFold and predicting a folded state, that's just a one-shot prediction problem where you have experimentally determined a lot of folded states and you use that as training data. But in molecular simulations, you really have to kind of simulate these molecules. You have to kind of model the dynamics. And so it's not this kind of one-shot prediction problem. You have to call essentially the MLIP many, many times. And that's where these inductive biases like equivariance is just very important. Okay, and so now there's this interesting question for also the people that I talk to from these domains is, given a particular problem, like for instance a particular atomistic system or a class of atomistic systems like molecules, what expressivity do I actually need? So for instance, how high do I have to put my L? Yeah, or and so there, for instance, I see very interesting connections. I talked to Mitja also about this. Instead of maybe just looking at the distances as kind of this input and what can we do, how much can we reconstruct the distances between the atoms in this case based on some form of message passing, what if we also allow the model to actually see the angular information? I'm not sure if there has been a lot of work on this, but this is something that chemists really care about because they would like to know how high do I actually have to go to really be as expressive as I have to be. Yeah? So this is something that's I think really interesting. And this involves a deep understanding of the problem and also, of course, some form of experimentation. But again, I think that is a really interesting problem. And this is a general theme. This even applies, in my opinion, to expressivity results when it comes to permutation equivariance. So the classic Weismeier-Lehmann stuff. How difficult is it actually to reach the known existing expressive model with SGD, or with any other types of optimization problems? So many of the proofs that we have seen throughout this workshop are existence proofs. They say there exists a particular instance of this model class, when we run one Weisfelder-Lehmann or whatever, and this is then equivalent to this particular fragment of a logic fragment or whatever. But actually, when we now train the neural networks, we actually optimize them using iterative methods. So the question is, do we actually get to this? Do we actually get to these very points that we need them to get to? And so this is, I think, something that is really lacking, and I think I also know the reason, because it's very difficult to study this and to understand and to think essentially expressivity. So kind of let's say the logical expressivity, the existence, also with the optimization jointly. So this is, I think, a really big challenge, but very important because this is what matters in practice. It's the same with universal approximation theorem for one hidden layer MLPs. That's nice, but typically they don't work if you train them on some problem, even though they are universal function approximators. And so kind of thinking these things together, I think, is really important. Then this is another thing which is more important to me. How do we generate the right data for the training? This is maybe not so important to this workshop. And then this also relates a bit to what Rizi was talking about. How do we actually implement and also kind of understand better these tensor products and contractions? So these are the operations that we need to run in these kind of equivariant message passing neural networks so that we can actually do this more efficiently. Because, and this is another point before I almost done here, one of the things, of course, that also matters a lot here is efficiency. Yeah, and so for instance, if you can reduce the time that it takes to compute these kind of message passing operations, and also if you can reduce, and this goes a bit, I think also maybe potentially back to your talk, kind of, you want to actually reduce your embedding size, so to say, yeah, as much as possible. Because the more you can reduce this, the faster you can actually run these simulations, which, yeah, in terms of when you use machine learning, are still much slower than these very crude simulations based on classical force fields. So they still take oftentimes far too long. Okay, so these are kind of like, I would say, there's really interesting kind of theoretical questions motivated essentially by this this problem. Okay, so this is where I would have started to talk a bit about this problem of thinking expressivity and optimization jointly. So where we actually have we proposed a method where you can essentially relax the equivariance and adaptively bring it back during training. But yeah, I will stop here. And like I said before, the goal for the rest of the session is to have some people maybe come up here, kind of say a few words also what they think an interesting problem was, what they learned in this particular workshop. Also for me, then what I will do is I will create a small document where we can kind of keep track of this and then maybe go back to it either to collaborate or to plan something in the future. So that's kind of from my side for now. Who is interested in maybe saying something now? There were a couple of people who have. Yeah, there are a couple of people who have volunteered. Yep. Yeah. I can use this.
Thank you.
I'll just take this off here.
No, you can. Yeah. So, okay. You can hear me, right? Good. So, first of all, thank you very much to the real organizers. I'm among them, but I didn't do really too much on the organization except for the day yesterday about the combinatorial optimization component, and that I wanted to just wrap up. I don't really plan to give you research directions or much, but I would like to just wrap up on what we have been seeing yesterday, because I think this was maybe the day in which there was more definitely, I mean, some of the connections with the one particular area in which graph neural networks can play a role. So we have seen, of course, 5 talks. So I gave an overview of the role of machine learning in general, but especially graph neural networks, the impact of graph neural networks in mixed integer linear optimization. I talked about the generalizations, requirements, and opportunities. Try to point out also what does it mean solving combinatorial optimization in a practical sense. Then we have seen GNNs with guarantee depending on special graphs. So the talk by Ellen, especially looking at this random geometric graphs, which I think actually seem to have a big impact also in practical problems, which which was a very interesting to hear. Then she talked about the algorithms with predictions, so where conformal and calibrated predictions role seem to be super important in order to actually make giving guarantees, which I think is a theme overall of this workshop, right? I mean, we wanted to try to exploit a graph neural network and use them to guarantee something. So I think this is actually has a lot of potential impact. Looking at specific type of graphs, some of them will be more useful for practical application than others, but definitely could have been also a way to go for mixed integer linear in general, programming in general. So especially motivated by the questions yesterday about what can we give up if we can get some guarantee and maybe solving using branch and bound as an approximate method, but with guarantees. So that, which I think is actually maybe through this conformal and calibrated predictions could be a very interesting topic. So Bartolomeo talked about first-order methods, and in particular the role of those first-order methods on the analysis. Yes, so the role of those methods in machine learning and potentially in mixed integer linear programming, and so formulated the problem of analyzing them. And there was a quick discussion on how GNNs could be actually becoming a tool in that area, which of course can be an interesting perspective. Christopher talked about expressiveness of ReLU neural networks, including the role of tropical geometry that is still kind of mysterious to me, but this morning I've been having more even connections. So potentially very interesting, lesser GNNs oriented, but of course networks in any case. And so this is actually like definitely food for thoughts. And finally, Axel talked about the role of GNNs in decision-focused learning, which decision-focused learning is one of the coolest, in my personal opinion, areas of the use of learning in discrete optimization. Just to remind you, the idea is to put an optimization layer at the end of a process of learning in such a way that oriented the learning over the fact that the parameters that you're learning are parameters for an optimization problem, which I think is actually the part that for a long while in the literature of combinatorial optimization has been missing. So there, the GNNs have been playing a fantastic role, and it seems also that they have they guarantee some convergence like the one that Axel was discussing yesterday. So I think this is more or less closes the loop. It's a wrap up. I'm not adding anything, but just to remind you what we have been seeing all together yesterday. And I guess my message here is, it's not exactly one community, but it's a lot of communities that they seem to, in this week, have been talking to each other very, very efficiently and effectively and pleasant, at least for me. It was a very pleasant week. So I would say that we should keep going. Thank you.
Yeah, if someone has follow-up comments or... I was kind of curious about the decision-focused learning, which you mentioned as a great application. So I'm also a bit aware of this. So what do you think is this, like a big problem there, right? So one of the things is kind of the backprop essentially through the...
So the work Axel is showing is the big problem, of course, is the differentiability at the very end, right? I mean, and then of course is if you're solving a combinatorial optimization problem, if you're lucky, it's the objective function is going to be piecewise linear, and so this is completely. The differentiability part, making this everything connected, workable with the stochastic gradient descent is the difficulty. There are several groups that have been doing different things. Yesterday, Axel shown one way of doing this particular thing. There are others, and depending on. I don't think we have yet a full let's say, understanding of what actually what is best. This is something that has started not too long ago, like 2-3 years. There have been a lot of efforts and certainly a lot of, let's say, successes on the way. I think it's actually very cool because this has been always in the back of the people starting the field, right? I mean, of using a machine learning for combinatorial optimization. When you're the classical objective function, so loss function of a prediction that has to be incorporated into a discrete optimization problem doesn't align with the discrete optimization problem. To me, it seems that the results by Axel are specifically oriented to this area in which indeed it was talking about stochastic optimization, so you don't know the objective function for sure, and that is actually makes things relatively easier than the extension that I was talking about yesterday on online problems is even more. But I can see many other situations in which you are predicting something that is actually like becomes the input of an optimization problem, and then you have to take into account that very much. And of course, I mean, connecting these predictions with some guarantees on what you're getting is of course fundamental. And this is actually connected to the work that also Ellen presented in the morning yesterday.
Okay. Any more questions concerning GNNs and combinatorial optimization? Comments? All right. Do you maybe want to continue, or?
Yeah, I don't want to impose myself, but I was asked to also share some thoughts. Yeah, I would like to thank the organizers first. It has been a very nice workshop. I think I learned a lot coming from a more theoretical perspective. I think it has been really nice to also dive into these more applied questions. And I think, people have a different way of thinking about things and different questions and different problems are arising. And that has been very nice. I would maybe in the end like to mention an open problem, or like recap an open problem that Ragai mentioned in his talk regarding expressivity versus complexity of GNNs. I think you had this figure with, I don't know which axis was which, but you had expressivity and complexity of different architectures, and like the idea would be to prove somehow what are the trade-offs between expressivity and complexity, or the other way around. Of deciding, for example, equivalence. So, like, just to make this more precise, I think a question that is still open regarding the Weisfeld-Liemann algorithm, which is classical in many ways, is whether the runtime of n to the k roughly is optimal for the k-dimensional Weisfeld-Liemann algorithm. So this would be an instance of this problem, and I think that would be very nice and far-reaching, whether we could prove an, theta of n to the k plus 1 lower bound for Weisfeld-Liemann. And then maybe to go further, I think homomorphism and distinguishability could also really help in that way. So if we take a graph class of, I can maybe write something on the board. If we take a graph class f that is like given in this form, so it's given by some formula and some integer k, and contains all the graphs f of some tree width that satisfy the formula. And you can imagine the formula being, monadic second order logic, for example. Then there is an algorithm for evaluating for checking homomorphism and distinguishability that runs in this time. And again, you could ask whether this is optimal or what sort of lower bounds you could prove. And Weisfeld-Liemann would be somewhat the starting point where the formula could be taken to be trivial. So that's the open problem.
So very interesting workshop. I have enjoyed it a lot, and I think it's a healthy community in the sense that theory and practice are interacting in a virtuous way, right? So this is not true of every community, by the way. So I would try to keep this being the case here. So I really, really appreciate this, that there is a very, very interesting interaction between what theory tells us and what practice tells us. So I would be very interested in trying to understand this question a bit more in depth. So I was thinking about something like this before. People have been looking into this retrieval augmented generation stuff, RAGs, right? That it's a way in which graphs can interact with LLMs to make them smarter in a way, right? And I've seen very, very little theory about this. And I think that this is interesting and precisely goes into this direction, right? So which kind of things graph neural networks can add to what LLMs are doing at the moment, yeah? So perhaps this is a nice area in which theory can say something, yeah?
How do you think symmetry awareness could explain RAG?
What?
How do you think symmetry awareness?
I can, sorry.
How do you think symmetry awareness could explain RAG?
No. I'm not claiming anything, right? What I'm saying is that symmetry awareness for me is what graph neural networks are doing, and then how graph neural networks can interact with LLMs to do something smarter than what we're doing now, right? That's my that's how I view this.
Yeah, just to also maybe reiterate on this point, like there is this big discussion right now, do you even need equivariance, or can you just run large-scale data augmentation?
For GNNs?
You mean, yeah, so this is mostly a discussion in the context of rotation,
Right.
equivariance.
That makes sense.
But when it comes to GNNs, right, so there is this thing that if you add these random, so if you break equivariance, right, then you get more expressive.
Yeah, but it doesn't work.
But it doesn't work. So the question is, can you kind of fix that, right? That it doesn't work.
This is a good question.
Yeah.
How to use randomness in order to come up with a GNN that works well and has good expressivity. I would say it's a good.
By the way, if you have pointers to where this kind of discussion is going on, it would be interesting.
Yeah,
So
I can
you
put this in the document.
Yeah.
I think it came up with the AlphaFold
Yeah, exactly. So
paper. So
yes.
they I think in one version they had an equivariant model, and then they removed it and they claimed that they didn't need it. From my point of view, I think that maybe for smaller groups which can be sampled efficiently, you don't really need equivariance if you have enough data. But for other combinatorial type of groups like SN and such, it wouldn't work. By the way, regarding what you said, there are some recent papers about knowledge graphs and RAG and stuff like that.
Yes.
Yeah.
Yes.
So people started to.
Yes. Not very theoretical though, no?
Right.
Yeah.
Not theoretical.
Yeah.
Practical.
Yes.
Would definitely set of interesting problems there.
Yes.
Yeah, there is a paper by Microsoft that uses RAG to generate a graph. So like you're generating a graph on the fly.
Yeah.
Yeah. Okay. Yeah. Do you want to maybe you had ideas to say like what could be
A follow-up event.
I know you told me that you are too honest and
No.
but I put you on the spot now
I'm
anyway.
not
So.
the right person to kind of wrap things up, but I know I really enjoyed the workshop. It was like most of you I didn't know before, so I was very happy to see all these different types of research going on. Very interesting. So I'm mostly kind of doing like the logical side of things, the expressivity, and that was like maybe a little bit, like we had the very nice bootcamp by Pablo, and then the connection to home counts by Tim. And like throughout the whole week, I've been kind of wondering like where logic could be used in other places. for example, in connection with the graph limits, the various graph limits that we've seen with graph fonts and things like that. So I think that's definitely maybe something that requires a little bit of collaboration between different people here in the audience to understand better like what are the specific things that we're looking at and what are our respective expertises. As a follow-up event, so initially we wanted to actually have like a longer program here in Simons about graph learning, and in particular with connections to theoretical computer science. And so it might be interesting if in the document to maybe also like highlight a little bit more specifically what are possible connections to TCS in case that we would plan to have like a longer program or try to again to have like a longer program here at Simons or at some other place. So if there is interest for that, please leave some comments in the document that Mathias will share. There was a lot of equivariance and invariance going on this week. So it seems to be a very important, if not one of the most crucial aspects underlying graph learning. So I learned maybe a little bit too much about it. But anyway, so I don't know whether this is a wrap-up. Maybe somebody can rescue me and take over before I start saying.
Would it make sense to try to make a white paper summarizing what has been discussed here, the different areas in which GNNs interact with? Because I haven't seen anything like this.
No,
right?
sure. At this moment, there are like like individual surveys about expressive power, about about the optimization part.
But not how these things connect to each other.
But not how this, or even like a very maybe higher level kind of overview, like where GNNs can fit in or slot in at the moment in different disciplines in computer science. Might be something that is kind of worth thinking about, definitely as a potential outcome of this workshop. We didn't plan that, but that's a very good suggestion. Thank you. Of course, somebody has to take the lead for that. So
that requires exactly that.
So the next person who takes over with the microphone is going to be. I'll throw it in the audience.
You're volunteering.
I have a question of a complete outsider of logic. But when Rizi was doing the talk and mentioning all these polynomials with different indices that are matched together, right?
Right.
I mean, that sounded complicated enough that to formalize some kind of logic model theory on these indices might be interesting. I don't know. I'm just asking as a complete outsider.
Sure, I think there are definitely connections also like to more than 3 variable logics or finite variable logics, the way that these things all interact. But I cannot give like a good answer to your question. We should ask.
One thing I was thinking I've also discussed with Bruno is people in logic have thought a lot about this semantics to syntax. I have a syntax and I impose some invariance property.
Sure.
What syntax does this force me into?
Mm-hmm.
Yeah.
And of course, database theory people have looked at this in the geometric setting in the past. Imposing geometric invariance on languages, formal languages that don't have them, and seeing what this forces to. And I think at least this is a place where there should be more interaction with graph learning than there's been so far. Of course, this is, Pablo results of Pablo do use some of these existing results, but not in the geometric.
No, that's true actually. Yeah. So there are potential connections indeed. Like in database theory, there have been gray languages over spatial data and invariances and things like that. So there might be connection. One other comment that I just remember is that like the logical perspective on graph learning. I mean, potentially it wasn't all itself like very important for to speed up things or to make things better, but it has been really a driving force to generate new models, right? Because every time somebody said like it has that precise logical expressiveness, then another group was trying to kind of beat that, to kind of add something, because it was suddenly clear what was missing from the previous model. And I haven't seen that particular aspect coming up so much in the other talks. Like it's more like like we assume some model is given, we analyze it using sometimes fantastic and deep mathematics, But then to go back to practice, like what it actually buys to kind of, as an incentive to improve an existing architecture, that is, this link I haven't seen so much, but that's maybe my misunderstanding or of these other areas. But that's something I think it was very nice, or is still very nice, about logical and more combinatorial approaches to analyzing GNNs. And that's me. Anyone else? Michael, do you want to?
Thinking back to when we were writing this proposal, one of the things we said we would do was we would look for areas of TCS where there wasn't much interaction, and we would try to sort of brainstorm. I mean, and mostly this workshop hasn't been about this. It's been people saying, oh, look, I did this cool thing that put in geometry or algebra. And so maybe, in the last few minutes, people can, I mean, there were certain places where there has been interaction, but we just ran out of time in the program for it. I think we've mentioned like communication complexity, for instance, is an area where there has been some interaction, but distributed computing, we thought about having a day for that, but we ran out of days. Originally, we had a notion that we'd have a few more days. Silence. But maybe if somebody wants to suggest areas where there hasn't been work yet, if you think from a TCS side, you would like to go down sort of the list of TCS topics and say, algebraic complexity, here's how it could be used in graph learning, quantum, cryptography. So if anyone wants to suggest something that we missed or that hasn't been developed yet, I think this would be a chance. Maybe you have your hand up, or it's just...
No, I was when you said algebraic complexity, or maybe circuit complexity more generally, I think...
But there is some interaction already, between...
Yes, but not very strong at this workshop at least.
Yeah, not at the workshop. I was thinking, there's things that we just ran out of time through at the workshop, but there's also things where so far because this is not a huge community, there hasn't been that kind of interaction yet, but there could be. Yes, Akiba.
He was talking about his library with tensor products and tensor network contractions. So I think quantum computing has done a lot of work on tensor network contractions because they do these like extremely large simulations. So I think it might be interesting to take ideas from their work in writing a more high performance like distributed computing library.
We talked, I think, maybe fine-grained complexity as an area where I haven't seen any interactions yet. But I mean, they're working on graph problems in general.
So the circuit complexity connection, could you say a few more words about that? So where do you see it? Like what's the connection to?
I mean, my biased view obviously is the expressivity of neural networks.
Okay.
In the sense of, neural networks are basically circuits, and I mean, I've been thinking about this from this feed-forward perspective, but maybe one can also do more in the graph neural network.
So the computation graph as the circuit, so to say.
Yeah, there could also be more. I don't know. Maybe
So,
someone knows.
I mean, Pablo...
circuit complexity in the sense of the pure transformers, but at least I don't see any works from the circuit theory.
Yeah. Pablo mentioned an enormous paper of Martin Grohe on the descriptive complexity of graph neural networks, which gives a connection of families of graph neural networks with a certain size bound at TC0.
Yes.
So that's one sort of data point in the area.
And there's also this recent work about connecting transformers to MPC model.
Mm-hmm.
Right, so you also have lower bounds, like how many rounds, how many processors, all this kind of stuff. So that's definitely something.
But this is a good chance to give some wild speculative conjecture of TCS. Is that?
I don't know. I don't think it's wild. Right? I talked about in the boot camp. I think that there's the analogy between MPNNs and WL, which we talk about, and I feel like I'm not a TCS person, but there are all kinds of other classes of graphs where you know how to how to solve graph isomorphism in such and such a time, and you could build a dictionary of like transferring all these insights from TCS to.
You mean like minor closed, look at what people do on minor closed classes, for instance, and to solve graph isomorphism.
I don't know what
and
minor closed
sparsity.
graph, yeah, but I don't know. I mean, I'm familiar with like, you know, graphs of bounded eigenmultiplicity or graphs with planar graphs, various things. So I don't know, like, you know, potentially, you know, one way to do it is to go one by one and try to sort of build a neural network that does this, but I don't know, like maybe you could also have some sort of theory of like what you need to do this nicely, or like take something like Naughty, which I always think is Naughty, the algorithm.
Sorry.
Oh, right?
Yeah.
So I mean, it always seems to. I mean, it's an
Well, there's
algorithm.
three
that
and
comes
one
from,
knows.
It comes from CS, right? But TCS, but I don't know. So it has very good ways to distinguish between graphs. And is that useful to plug it in somehow? Can you plug it in and make a better GNN? I don't know.
This has been done to some extent.
Yeah,
I can point.
Okay. I know that it has been done to some extent, but yeah.
Is there an architecture that can implement a Babai's algorithm for checking graph isomorphism, for instance? Which, by the way, it's not published yet. Huh? You know that Babai's algorithm is still under review. But like these algorithms are, I don't know the algorithm, but what I've heard and what I've read is that it's mostly based on spectral information about the graph, right? And how much GNNs can integrate this spectral information somehow in the analysis. No?
So for the ignorant, what is particular about this algorithm? I never heard of it. So
Yeah, it's a quasi-polynomial time algorithm for checking graph isomorphism, right?
Purported.
Huh?
Purported.
So it's recent? Or it's
8 years, 10 years.
Yeah.
It's not
10 years, but still not confirmed.
Yeah.
It's
Under
not
review.
confirmed.
So
Yes.
why do we know why it's not yet confirmed? Nobody wants to do it, or?
Let's take it off.
Why not?
I think so.
Going back to your sort of solicitation for potential TCS-related topics, I guess as someone who's been a member of the TCS community, I think some other things that come to mind, which I don't think have been mentioned, probably property testing. That's one area that has been quite popular in TCS, particularly for graph properties. I would say also maybe.
So proper testing the connection, you're just saying this is an area that could be connected, or you have some connection?
I mean, don't ask me too much questions on exactly what the roadmap for that is, but I think it's a. I mean, for those.
I wrote a paper about this. 2016.
Oh, did you? Okay. We should talk then.
In 2016?
Graph property testing and graph learning.
Okay.
Okay. No, I'd love to.
That's it.
I'm not familiar with it.
That's it.
Check.
Okay.
Is that the first and last paper on the subject?
It was pretty comprehensive.
Sorry, go on.
Well, because I mean, just an aside as a joke, right? They say when you're starting a PhD or something, how do you decide a field to get into? Well, you should either publish the very first paper in that field, or the best paper, or the last paper. So I think the first one of those is usually the easiest. But going back though, property testing. I think streaming algorithms and related to that sketching.
Yeah.
I know there was a talk yesterday, I guess maybe it was Ellen's, that talked a bit about online algorithms, but there's a slight distinction there. So I think those are probably settings where there can be some interplay between these communities.
Yeah, an area that is very, I think, on which there is a lot of activity in theoretical computer science is this area of algorithms with predictions. So this is definitely the part in which one part in which potentially there will be a lot.
Yeah, I think this learning augmented kind of algorithms like that I think actually seems like a potentially practical.
And Alan also mentioned this in her talk, like bringing these two communities together, neural algorithmic reasoning and algorithms with predictions. I think that's important for meaningful.
I'm still waiting for that bizarre idea. Okay.
Well,
chair.
I guess it's actually, it is exactly 5. So we've made it. Yeah, I mean, I think I can speak for all of us. We had a fantastic time. So thanks again to the organizers. Yeah.
Just one last word. I actually want to especially thank Christopher Morris. Like, he has been really doing most of the work and all the heavy lifting, all the communication with most of you probably. So Christopher, thank you. Yeah, and thanks for coming and giving nice presentations and staying awake during them. That's very much appreciated. Okay.